we do the exact same thing. So multiply these two together, and then subtract it from these two multiplied together. So using theorem, we know that c squared minus c cannot be 0, right? Because if it was 0, it wouldn't be invertible. Okay, well, from there you just factor out c minus 1 equals, it cannot be 0, or in other words, c cannot be 0 or 1. So, I mean, that pretty much solves the solution. So, one thing I want to point out is from, as you guys might be telling, a lot of the things that I'm doing now might are starting to become a lot more, I guess, abstract. Do study, look at the theorems and what they say. Don't like memorize what it says. Look at the big picture of what it says. So, how I always like to remember the theorems is I always like to say, okay, what is it saying, and how can we use it, and always come up with an example where you can use it. So, for example, this example, use the theorem, right? It use one of the statements. So when you look at these, look at the or study, um, always look at the big picture, and always try to come up with an example that you can use the theorem, okay? Because it's gonna start, we're gonna start using a lot of this stuff or rule or results in well coming in these coming sections. It's not longer just gonna be, oh, solve this system, or obviously there'll be some like computational problems, but it's gonna be a lot more conceptual now. Okay, so now let's finish off the section with uh, 3 or 4 theorems. I'll state quickly. So this would be theorem. Where'd it go? Oh yeah, there it is. So I think what this one was 2.32, 2.33. So this one says if A is invertible and then the inverse is unique. So again, what is this saying? It means that, so before I was just telling you this is the inverse, right? How do I even know that this is the only one that can do it, right? So this theorem actually states that it's the only one. Unique meaning uh, one, right? So again, I'm just gonna write a quick proof of it so you guys can like kind of see how to do this. So it's not bad at all. So basically, this is another contradiction one, right? So suppose instead of only having one, suppose you had two. Suppose B and C were inverses of A. Okay. Okay. What does that mean? If you remember the definition, that just means that AB is equal to BA is equal to the identity, right? And also that AC is equal to CA is equal to the identity, right? We know this. So all you have to do at this point is basically, I guess, let's see, how can we do this? So we want to show B is equal to C. So observe that B, right? What is this equal to? Well, it's just equal to B times the identity, right? So remember, a matrix times the identity is just that matrix itself. We saw that, right? It's like a 0 for numbers, right? So the number plus 0 is this number itself. This is the same thing. Or a number times 1 is itself. Okay, but what is this? Well, that is the same thing as, we can say, this guy right here. Sorry, this guy, right? I mean, that's equal to the identity. We just said that. So this is just B times A times C, right? But we also know that matrices associate. So we can associate this times A times C. But what is b times a? Well, it's also I. So this is also I. So that's just going to be equal to I times C, which is equal to C. So the entire time B was is equal to C, which means it contradicts our assumption that B and C were different. So that pretty much proves that. Okay, so these next ones I won't prove it, but again, I just want to get you guys used to like seeing these things and how the logic works. But yeah, so that all that tells us that is the inverse is unique. So the next one. So I think this one. Okay, and then we're going to discuss three last properties for inverses. I won't prove these, but it would be great exercises anyway to prove. So let's say you had two square matrices that are invertible. Then A times B is invertible. And okay, so now that we established that AB is invertible, what is actually the what is it really? So this is just going to equal to B inverse A inverse. Okay, so you can imagine just like switching them and then taking their inverses. There's a homework problem that uses this fact. So it tells you find AB inverse, right? And it just tells you to fill it in. Well, you can use this guy right here to just find the inverse of B and the inverse of A and just multiply them together, and you can solve it that way. Okay, next. 2, 3, 5. So if C, a square matrix, is invertible, then the following are true. So so A times C equals B times C. So remember how last time I told you just because these two matrices are being multiplied doesn't imply that A equals B? Well, if C is invertible, that does indeed apply. So this does imply A equals B, okay? And then same way as the other, same argument for the other side. So C times A equals C times B implies that A equals B. This proving this one is actually very trivial. It's not that hard. Okay, and then last but not least, we're gonna give you the whole point of wanting the inverse, at least in the context of what we're doing. So this last theorem here is gonna be useful. So theorem 2.3.6. So if A is a square matrix and invertible, then the system AX equals when we I'll actually have 2 days of review, and I'll send out a review to all of you. And I guess if the people who have already taken me before already know kind of like what the format with everything will be, so with the test. So anything that's on the test based on the review will basically give you like 80 to 85% of the test. Like if you can do the review, you should be able to score at least a B. The rest of it to score the A, you have to like do your own kind of thing and earn that A. So so don't worry about I guess failing the failing tests. If you can do the review, which I'll do with you, you can pass the test. So where was it? Oh yeah. Then this system has a unique solution. And the solution is literally just x equal a inverse b. So remember how I said you can divide by a and just solve for b? Well, this is the analog of that. Now you can, in order to get from here to here, all you have to do is multiply both sides of this equation by the inverse, like this, right? And then this will be the identity, which will just give you that, and that will just give you. So that's the whole point of this, the inverses. If your matrix A is invertible, then you can just multiply both sides of the matrix equation by A inverse, cancel it out like division, and just end up with this, which you can compute. You can compute A inverse using the I guess the trick I showed you, and then multiply by B, right? So that's the whole point of this entire thing. So let's do maybe just let's do an example now and finish off the section. So example 2.32. So solve, let's say 2x plus 3y plus z is equal to -1. 3x plus 3y plus z is equal to 1. 2x plus 4y plus z is equal to -2. Using theorem 2.3.6, okay? So we're gonna, I mean, you can do RREF and solve it that way, but I just want to show you exactly how you can do it using the guy I just stated. Okay, so first and foremost, all you gotta do is just set up the matrix equation, right? So let me move. I guess I should maybe copy this over here. So solution. Okay, so setting up matrix equation. So you get 2,
I did
3,
pretty good.
1,
I didn't die.
3, 3, 1, 2, 4, 1, x, y, z is equal to -1, 1, and -2, right? So all you have to do now is, so this is my A now, right? So we need to find A inverse now, okay? So remember, all you have to do is literally just do A, and then since it's a 3 by 3, take this adjoint matrix, RREF it, and you should get, if it's invertible, and which in this case it is, you get this guy, right? So so we get, so I'm just gonna skip that part. You guys know how to RREF it already. So if you do all that, you get -1, 1, 0, -1, 0, 1, 6, -2, -3. Okay. So that means now all you have to do is multiply both sides of this equation by that, and you get the solution. So we get, so x is going to equal x, y, z, which is equal to A inverse 1, 0, so 0, 1, 6, -2, -3, times b, which was the -1, 1, -2. So if you do the matrix multiplication here, you get, well, it's just going to be -1 times -1 plus 1 times, so it's just going to be 2. Second one is going to be, so again, you guys notice what I'm doing. I just multiply this with with this, right? So -1 times -1 is just 1, plus 1 times 1, which is 1. So 1 plus 1 is 2, right? So you keep doing that with every single one. So yeah, so in the end, you're just gonna get -1, -2, and there you go. That's your answer. Right. So good. So now we have another way to solve matrix equations, right? So we have RREF. We have now this way if A is invertible, right? If it's not, then you can't. So for those systems that, so this only works if you have a unique solution. It doesn't work if you have infinite unique solutions, right? So remark. Um, this only works if A inverse exists, obviously, or in other words, uh, or you have a unique solution, which comes with that, right? So you can't always do it, is my point. Okay, perfect. So again, let's give a quick recap. Of what we did. We started off with wanting to solve systems of equations. Clearly, if the system's too big, then it becomes very complicated, right? So then we started using some objects called matrices. These matrices contain the information of the system of equations, linear, right? And that information is just the coefficients. Okay, so once we had that, then we started talking about ways to solve the system using operations on matrices, which was RREF, right? Or REF. We saw different ways, we saw different things that could happen. We have no solution, infinite solutions, and a unique solution, right? Then we talked about basically, well, I guess more theory, like I guess justifications of why we're allowed to do it. But then for this one, this section at least, we started talking about a different way to solve the system, right? So usually we just converted the matrix equation to an augmented form, or augmented matrix, because we didn't know how to solve AX equals B yet. But now now that we see that if A is invertible, the coefficient matrix, all we have to do is just find the inverse, multiply the equation by the inverse, and you solve the equation, right? So yeah, so that's basically, I guess, big picture thing of what we've done so far. Okay, so now next section. This next section is called what's 2.4? It's called elementary matrices. Okay, so this is what I mean by it's going to get a lot more conceptual. Yeah, sure. So from now on, you should really start doing that. What, or at least I don't know. However you learn is depend, but like basically try to like find a way to like really conceptualize everything we're talking about, because these once I get to this and once we start talking about determinants and vector spaces, it's you might want to have something like a big idea picture or an explanation of what we're doing, kind of thing. But yeah, so elementary matrices. So this section is basically, if you remember how we were doing row operations, you know we were just like like interchanging rows. I was just multiplying the rows, and I was just adding rows, and I didn't really tell you why can I even do that, right? Or how do you even do that, like without like I guess manually doing it. Like for example, how would you tell a computer to do that? Well, you can't just I mean if you do programming languages, you can't like just say do this, right? You have to work within the language. But so this is basically going to make all that formal. Okay, so recall the three elementary row operations. So we will see in this section how to make this formal. Okay, so let's first define what an elementary matrix is, and this is what it is. So a matrix, let's say square matrix E, is called a elementary matrix. If I guess if it can be obtained from the identity matrix by a single row operation. Meaning, if I take the identity, one's in the diagonal, if I just do one operation, for example, let me just interchange the first row and second row. Well, that single operation would make an elementary matrix. Or, for example, if I scale one row by 2, that would be an elementary row matrix. So as long as I can obtain that matrix just by one operation, then it's called elementary. So let's look at some examples of that. So, question: which of the following are elementary matrices? So let's look at this matrix: 1 0 0 0 3 0 0 0 1 1 0 0 0 1 0 1 0 0 0 0 1 0 1 0, and this one 1 0 0 0 2 0 0 0 minus 1. And remember the identity, I guess in this case the identity is just a matrix with ones in diagonal and 0 everywhere else, right? So just keep that. Okay, so according to the definition I just gave, is number 1 a elementary matrix? Yes, right. Why is it? Because how can I obtain this matrix via one row operation, like from the identity? 3, yeah, exactly. You multiply the second row by 3, and you get this matrix, right? What about the second one, number 2? I mean, what? So the identity matrix has to be, first of all, square, but in my definition, what did it have to be? A square matrix, right? Is that thing a square matrix? No. So this one, so let's put it. So this one is a yes. This is a no. What about that third one? Yeah, because all I have to do is do what? Interchange the second and third row, right? From the identity matrix. What about number 4? No, I think I heard. Yeah, no, right? Because yeah, I can make the identity matrix look like this, but I'm gonna have to do 2 operations, right? I have to multiply the second row by 2, and then the third row by -1. And remember, the definition just means I have to obtain it by one single one. So yeah, perfect. So okay, so now let us see what elementary matrices actually do. So let us see. what elementary matrices do. And we'll do that by using an example. So example 2.4.1. So let A equal, let's say, A, B, C, D, E, F, G, H, and I. Let's have this elementary matrix E1, and let's have it be 0, 1, 0, 1, 0, 0, 0, 0, 1. And let's have E2 equal 1, 0, 0, 0, 1, 0, 0, 0, 5. Okay, so let's compute E1 times A and E2 times A. All right, so let's just do that, right? So let's have E1 times A, which is going to equal 0, 1, 0, 1, 0, 0, 0, 0, 1, A, B, C, D, E, F, G, H, I. All right, so if I do this, what's going to happen? Okay, well, we already know how to multiply matrices, right? So let's multiply that. So 0 times A is 0, 1 times D is D, so that gives me a D right there. 0 times D is 0. Okay, now let's do the second row. So do that one with this one. All right, so that's going to give me B, 1 times B, which is B, 0 times E, which is 0, 0 times H, which is 0, so it's just going to be B. Oops, sorry, my bad. So, sorry, hold on. I should do the other one, so hold on. Wait, what am I doing? I'm still in the first row, sorry. So 0 is, I'm still going to be right here. So I'm still right there. I was like moving ahead, which I shouldn't have. Okay, so first row in the orange column. 0 times B is 0, 1 times E is E, 0 times H is 0, so this is going to be E. And then let's do it with the green column now. So 0 times C is 0,
yeah, no,
1 times F is F.
No, not him, the other guy that joined.
Oh, the other guy.
Okay, so
I'm trying to be quiet
and
for
then
the
we'll continue this way, and if we
class.
continue this way, what are we gonna get? So we'll get A,
I got about like
B,
another
C,
20 minutes, so I'll be back
G, H, I.
around then.
Sounds good.
Okay, so now let's talk about what just happened. So for this one, this matrix, the original matrix A, and this new one we just obtained, what's the difference between both? Yeah, exactly. We switched the top row and the second row, right? So this elementary matrix E1, what it did is it interchanged rows 1 and 2. Okay? So this is how we formally do it. We don't, this is where we were even allowed to do it in the first place. But right, so now you're gonna see the next one as well. Elementary matrices are the row operations for matrices, right? So, for instance, this one changed rows. Other ones could multiply rows by its constants, and other ones will add multiples of rows to another. That's what elementary matrices do. They just do the row operations we already talked about. But let's just do the last one. So let's do E2 times A. So 1, 1, 5, 0, 0, 0, 0, 0, 0 times C, D, E, F, G, H, I. So if you do all the multiplication, this is what's going to end up happening. So A, B, C, D, E, F, and then it's going to be 5G, 5H, 5I. So this one did the exact same thing. It just scaled the third row by 5, right? Okay, so let's, I guess, talk about a little bit about patterns here. So I think in week 3 homework, they make you write matrix, like the row operations via these matrices. So we'll do examples on that right now. But first of all, I just want to talk about the patterns here. So I'm going to try my best to explain the patterns, but when you work with these, you'll start seeing them. But basically, if you want to interchange rules, look at this matrix here. So see how, sorry, over here, let's just look it over here. E1. This one interchanges first row and the second row, right? So basically how I view it is this way. If I wanted to interchange the second row and the first row, this first row, if I always call this like the, so like say 1, let's say 1, 2, and 3, okay? The position I put the 1 in is where that row will go to. So that first row right there, if I wanted it to go to the second row, I put the 1 into second position. Same thing with this one. I wanted this row to go to the first row, so I put a 1 in the first position. And then since I wanted to keep the third row unchanged, just keep the 1 in the third position. So that's the pattern. That's how I think of it at least, right? That's how you interchange rows. Same thing with this one now. You can think of it the same way. So if the ones or any numbers in the diagonal, what that's going to do is going to keep the rows the same. But if you put a different number in it, for example, this one, and again, and this is the first, second, and third position, what it's going to do is it's going to keep the third row in the same position, but it's going to scale it by 5, right? So as you practice these, just come up with your own like way of like seeing this. I don't know, this is how I see it, or when I do these at least. All right, so now that we know this, so let's do an example now that is like relevant to the homework. 2.42. Find a 3 by 3 matrix corresponding to the row operations R3, scaling that R3 by R3. So, and then we want to replace R2 by negative R3 plus, oh sorry, R1 plus R2. I guess I could just do this, I mean, be less confusing, just be R2 minus 3R1. And then last but not least, let's interchange row 1 and row 2, okay? So solution. So just keep track of everything. So 1, according to the explanation I just gave, right? So the only thing I want to do with the first row operation is scale row 3 by negative 7, right? So like I said, keep the positions the same. So I'm not going to do anything to the first row. I'm not going to do anything to the second row. But the third row, I'll keep it in the same position, but I'll scale it by 7. Okay. So that's how you do that one. Let's do 3, because that's the other one I talked about. Okay. So again, 1, 2, 3. All right. So I want to interchange row 1 with row 2, which means that I want this row to go to the second position. I want this row to go to the first position, and I want this to just stay the same. So that's how you do that one. And then number 2. So okay, so how do we add rows? Okay, so same logic applies. So we can do the same thing, like 1, 2, 3. So since we're replacing row 2, we're not going to do anything to row 2. So you see how here we're just going to be changing row 2. I won't be doing anything to row 1 or row 3, so just keep those the same. Okay, so now what I'm going to do, okay, so same logic. So what I'm going to do is for row 1 in the first position, I'm going to take -3, and then I'm going to add it to row 2 like this. So again, this is my way of thinking of these things. You can come up with your own, but at least this will give you some, idea of where to start. So this is how you come up with these elementary row operations. You can always just view them as like how we just did it right now. Okay, perfect. So now let's go to the next thing. What is it called? So let's see. Let's actually do a problem. So now let's take a matrix and reduce it down to REF. Okay. So we're gonna write down the row operations, and then right after, we're gonna write down the elementary matrices corresponding to those row operations, and then we're gonna see how we can express that as matrix multiplication. Okay. So let us see how to express row operations using matrix multiplication. Okay. So, and I'll be illustrated with this example. So 2.4.3. So I guess find a sequence of elementary matrices yeah, I can explain it at the end, I guess. So because I have like a few minutes left. That can be used to write A in REF. Okay, so A is going to be 0, 1, 3, 5, 1, minus 3, 0, 2, 2, minus 6, 2, 0. Okay, so first, okay, so if the question asks you to express it as a product of elementary matrices, this is the first thing you can do. So just do the normal RREF first. So let's start off with 0, 1, 3, 5, 1, minus 3, 0, 2, 2, minus 6, 2, 0. Okay, so again, how do we do this? Well, always look at the main diagonal, make everything underneath the 0, and everything under the diagonal 1, right? So first thing I'm going to do is I'm going to interchange the second and first row. So row 2, interchange with row 1, right? So I'm just going to have 1, minus 3, 0, 2, 1, minus 3, 0, 2, 2, minus 6, 2, 0. Okay. Oh, wait. I just copied something down straight from there. So 0, 1, 3, 5. Okay. Again, all right, so that 1 is still 1. So the next thing I'm going to do is R3. So R3 minus 2R1. And that will give me 1, minus 3, 0, 2, 0, 1, 3, 5, 0, 0, 2, negative 4. And let me size this. Okay, so we got rid of that. So now, yeah, so we got rid of that guy. So now we just make that that 2 of 1. So row 3, replace it with 1/2 row 3, right? So 1 minus 3, 0, 2, 0, 1, 3, 5, 0, 0, 1, minus 2. Okay, so this is REF, right? I wasn't doing RREF. Okay, so from here, just label each of those row operations 1, 2, and 3. Okay. So from here is what we're gonna do for what we did with the last example. So I remember the last example I just wrote down the elementary matrices. Same thing I'm gonna do right here. So let me copy all this and let's move on to the next page. So here it is.
I think the sketchy website I bought this turtle from stole all my info.
For one,
Ooh.
How do we express this as an elementary matrix? So again, E1 is going to equal, well, it's going to be, sorry. So I'm going to interchange the second row with the first row. So I'm going to do, so again, label your positions. So I want to put the first row in the second position, put the second row in the first position, and leave this one alone. Okay, what about E2? Well, that was R3 minus 2R1. So again, 1, 2, 3. So I'm not going to do anything to the first 2 rows, but I'm going to then take R3 and then multiply by -2. So that's how you do that. And then E3, I need to scale the third row by 1/2. So these stay the same, and then the third row I'm just going to scale by 1/2. Okay, so if I want to express what I just did by hand, so again, so this guy right here was my REF form, right? And this one right here, where is it? And this guy right here was my original matrix A, right? So now let's express this matrix that I have in orange as a product of E1, E2, E3, and A as follows. So that means that, so what is the first thing I did? Okay, so I took A and I performed E1 first. So when you do multiplication of matrices, you always want to do I guess from the inner and then outers, right? So you did E1 first, right? And then after you did that, you did E2, and then after that you did E3. So this matrix is exactly that orange matrix that we got. So the 1, -3, 0, 2, 0, 1, 3, 5, 0, 0, 1, -2. Okay? So that's this orange matrix that I got right there. So notice that everything we did by hand can be expressed formally as a matrix multiplication of elementary matrices. No. So eigenvalues will be at the end of the semester. E here is elementary matrices. I guess if I do the upper index, I would mean the eigenspace and eigenbase, but you'll see those later. Not right now though. Okay. Let's see, what time is it? 46. Okay. Okay, so now you're starting to see, okay, again, why are we doing this? Well, again, all of this is conceptual things. We're going to use these things to formally define things later on, and then finally you'll start seeing application problems, I promise. We just have to build enough stuff in order to get there. So let A and B be square matrices, or not square matrices, let's just say they're rectangular. So now we can actually, you could, but it'll be counterproductive because you won't be able to see what the elementary matrices are. You could, but keep them separate because we're going to use those later on. So, okay, so now we can finally rigorously define when two matrices are row equivalent. So a matrix B is row equivalent to A if there exists a sequence EK, a sequence of elementary matrices, right? Such that with B equals EK times EK minus 1 all the way to E2, E1 times A. So basically what we just did, right? So that last example, I will explain that right after class, which is like in a minute. So this matrix A right here is row equivalent to this orange matrix right here, all right? Because there existed a sequence E1, E2, E3, such that it satisfied this definition, okay? Okay, so I guess at that point, I guess no challenge question today since we didn't get to the part that I needed to. But yeah, any questions so far? No? Okay, well, it's 50.
Yes, I have a question. I'm sorry. Can you go back to your previous slide? Yes, explain the E's again. That's why I lost you.
Like explain them, like as in how I got them, or what?
All right, so E1, I see that you just changed row 3 with row 1. It's okay.
Right.
Or row 2 or row whatever. Right. Okay, explain E2. I don't understand where you're getting the -2 from. That's where I'm getting kind of confused.
So the -2 comes from the fact that we scaled row 1 by 2. So you see how -2 is in position 1, right here.
No, I don't see your -2.
It's like it's in position 1 in reference to the column, right?
Yeah. Oh yeah, I see now. So
okay. So I scaled row 1 by -2 and then added it to row 3. That's basically what this.
Okay. Yeah, because that -2 and that 1 were kind of throwing me off. But okay.
Yeah. So that's how you do. Again, you figure out how you can think of these things. But that's how I like think of them. But yeah, that's where that came from.
Oh, okay.
No? Okay, perfect. You guys are free to go. I can't keep you here anyway, so.